So a quick outline. First, I'm going to recap shortly on what MQ really is. Then I'm going to introduce the trapdoor and cover the attack that comes with the trapdoor and other attacks which we also defend against. And then quickly I will estimate security and show some details of the implementation. So multivariate quadratic cryptosystems, the idea is that your public key is a set of multivariate quadratic polynomials. And so the entire world sees only the part that is above the dotted line, which is a single set of public polynomials, which is difficult to invert, obviously. On the other hand, the person with the private key can first invert a linear map T, then invert a secret quadratic map F, and then invert another linear map S. So the person with a private key can obtain pre-images. And multivariate quadratic cryptosystems come in two flavors, single field schemes and mixed field schemes. And the canonical example of a single field scheme is UOV, in which there is a partitioning of the variables in oil and vinegar variables, such that oil variables are not mixed with oil variables, and this property allows the secret key holder to efficiently find inverses for given images. Namely, you fix the vinegar variables at random, you obtain a linear system, and you solve the linear system to obtain O. OV can then be turned into a signature. The canonical example of mixed field systems is HFE, in which there is a embedding function. So you identify vectors of base field elements with extension field elements, and that's what phi does. And then once you have an indeterminate over the extension field, you can define a polynomial over the extension field and use that as the central thing in your crypto system, as a central map. So in order to invert this, you have a polynomial expression equals y, you move y to the other side, have a polynomial expression equals 0, factorize that, and you have the roots, which correspond to signatures. But both of these schemes are signature schemes, and we want to talk about encryption schemes. So the first encryption scheme is ZHFE, and the idea is instead of one polynomial over the extension field, there are two polynomials over the extension field. And both polynomials have a very high degree, but there exists a third polynomial, psi of x, which is a function of the first two. So in order to invert a given image, a given ciphertext, you compute the function, the value of psi of x from the function values of f and hat of x, and then factorize psi of x, and then you obtain the unique plain text. So that's one encryption trapdoor. Another encryption trapdoor is ABC. The idea is to embed matrix multiplication inside your secret map. And then by cleverly combining two components of your secret map, you produce a linear system such that if you solve the linear system, you obtain the plain text. I'm going to put this away for a sec. So what we propose is extension field cancellation. The idea is we have two high-degree polynomials in our secret map, and by cleverly combining the high-degree polynomials, we end up with a linear system, and if we solve the linear system, then we obtain the unique plain text. So you can think of it as lying in between ZHFE and ABC. It's worth noting that all three maps are expanding maps. This is sort of necessary if you want to do encryption, because if you want to do encryption, you want unique recovery of the plain text, and that means your map has to be injective, and if it's injective, it has to be expanding, because if it's not expanding, you can distinguish it from random using differential methods. So what does the trapdoor look like? Of course, we're going to need the embedding function, and as I'm going to present this in two ways, in one way over the extension field and in the other way over the base field, we may want to use the matrix version of this embedding. So a vector of base field elements can be a single extension field element, and we can also think of it of this extension field element as a matrix of base field elements. So we choose A and B as random n by n square matrices, multiply the vector of indeterminates into this, and lift that to the extension field, and that's alpha of x and beta of x. Alpha of x and beta of x are essentially linearized polynomials. So then the central map is really, really simple. It's alpha of x times x in the first component and beta of x times x in the second component. That's the description over the extension field. Over the base field, we have this matrix times vector multiplication. It's worth noting that these matrices commute, which is exactly how we invert. Because given that they do commute, we can multiply the first equation by beta of x, multiply the second equation by alpha of x, and then we have exactly the same expression. We subtract the two expressions, equate to 0, and poof, we have a linear system. And once we have a linear system in the plaintext x, we can solve it, and then we have the plaintext. So that's nice. And there's even a small enhancement that we can do to improve it. Namely, that's the Frobenius tail enhancement or modifier, which is adding an extra term. This only works in characteristic 2 or 3, unfortunately. But nevertheless, it's very neat. So inversion happens the exact same way. We multiply the first equation times beta, the second equation times alpha, and because this power 3 becomes power 4, and 4 is a Frobenius power in the characteristic 2, the expression is linear, right? The first term is the same, so that cancels, and poof, you can solve a linear system and obtain the plain text once again. So, unfortunately, we are using a bilinear relation to do decryption, and that paves the way for a bilinear attack, the same attack pattern used to break C* back in the day. So this bilinear relation holds for all plain text and ciphertext pairs, and it doesn't matter that we sandwich the secret map in between two linear transformations, because such a relation will always exist, meaning that such coefficients in a polynomial in x and y will always exist. So if you generate many, many, many random plain text, compute the ciphertext, then you have a very large system, linear system, in these coefficients. You compute these coefficients, you've got this polynomial. And once you've got the polynomial, you can invert any given image easily by plugging it in, and then you obtain a linear system. So we definitely want to block this attack, and we do that using minus, which is a modifier, and I'll explain in a minute. Essentially, minus consists of removing polynomials from the public key. And it so happens that minus also thwarts the algebraic attack, which is running Grosvenor basis algorithms. So we definitely want to use minus, and we also want to use projection to block a linear differential symmetry attack if it should be applicable. So what does the algebraic attack look like? Essentially, it's running Grosvenor basis algorithms on your polynomials. And what Grosvenor basis algorithms do is they create a very large matrix in which every column represents a monomial and every row represents a polynomial. And the algorithm is going to expand this matrix by taking polynomials and multiplying this with monomials. So then you get a new polynomial, so each time you add another row, and sometimes you need to add other columns because the degree of your polynomials increases. And so the running time of this matrix, of this algorithm, depends on the degree of the polynomials inside it, which is the degree of regularity. And it so happens that the degree of regularity is linked to the quadratic form, the rank of the quadratic form of the extension field description of the map. So if we associate with the extension field indeterminate x, this vector, x, x to the power q, x to the power q squared, and so on, then we can describe the secret map, or the public map for that matter, as a pair of quadratic forms. And the rank of these matrices is linked to the degree of regularity. So let's visualize this for a second. In the first component, we have alpha x times x. Alpha x is linear, x is linear. We multiply the two, so we have a rank 2 quadratic form. The next step is to apply the input transformation S to this matrix, and that's essentially a change of basis. So that doesn't change the rank of the quadratic form. So I chose to draw these matrices in the most conducive to understanding basis, which isn't necessarily equal to what it says to the left. So essentially appending this, composing with S doesn't change the quadratic form. Fortunately, composing with T does change the quadratic form, because we can think of T as raising your indeterminate to subsequent Frobenius powers, weighting them, and then summing them. And if we consider the quadratic form in this vector space, in which every column represents the next Frobenius power and every row represents the next Frobenius power, then it boils down to taking this small square, shifting it to the right, down, weighting it, and repeating that. Shift to the right, down, weight it, and then sum it over everything. And then you get this band over the diagonal, which does increase the rank. So you might say, hooray, we're done. Alas, no. So that's exactly what Grosvenor bases are really, really good at. They implicitly recover the output transformation T, and then it starts expanding the matrix, but it will be done very, very quickly because your rank is very small. However, if you drop polynomials from the public key, then essentially you're dropping rows from T. And because the Grosvenor basis algorithm doesn't have this information, it cannot recover the smallest possible square. So at most, the smallest possible square it will recover will be larger by the number of rows you drop from T. So dropping polynomials from the public key will increase the running time of the Grosvenor basis algorithm. And that's validated experimentally. Here we fixed the parameter n and looked at the running time of the algebraic attack for various numbers of dropped equations. And while this may not be as even as we had hoped, it's certainly, the trend is clear. Of course, removing information may lead to decryption errors, but thankfully, these decryption errors drop way before n becomes relevant. So in practice, n will be 80, 100, 200 maybe, and a will still be the same, so we don't really have to think about decryption errors. So then there's the differential symmetry attack, and it probably does not apply to our system. Nevertheless, it makes sense to inoculate our system against this attack because inoculation is free anyway. What PS does is to choose S to be singular and N to be prime. This way, it ensures that there cannot be a subfield. And we emulate this by choosing A and B to be singular and N to be prime. Moreover, the kernels of A and B should intersect only in the origin if you want to ensure unique decryption, with high probability. So that brings us to estimating security. We're going to estimate the complexity of the Grosvenor basis attack. And essentially, the Grosvenor basis attack creates a large matrix with many polynomials. And the number of polynomials is n choose degree of regularity because these monomials have degree of regularity. So that's t. And then in every row, we're only going to store the non-zero coefficients. And as these arise from the original polynomials, this is n choose 2. So given t and tau, we can estimate the complexity of sparse Gaussian elimination, and that's tau t squared. And then there happens to be this upper bound on the degree of regularity, which experimentally turns out, it turns out that the degree of regularity does exponentially tend toward this bound, so that we can use these formulas to estimate a degree of regularity, and in particular, we propose these parameters. It's worth noting that if we do use the Frobenius tail, that's what this t square stands for, then we have to drop 2 fewer equations because the rank is naturally higher. So you might say A is intricately linked to the degree of regularity. Why don't we increase A by a lot? And the problem is the decryption algorithm is exponential in A. The reason is for every polynomial you drop, you lose 1 bit or 1 trit of information which you need to establish the linear system from which you're going to compute the plain text. And if you lose this information, you have to guess it before you can even start solving the linear system. So you want to keep A as small as possible. On the other hand, as n increases, the complexity of the algebraic attack also increases, which is exactly what you would expect. So, implementation results, it's worth mentioning that encryption is really, really fast. On the other hand, decryption is not so fast. In the case where we use the Frobenius tail and we drop 2 fewer polynomials, decryption is almost 4 times as fast because we have to guess 2 fewer bits. Also, the public key is rather large. So that brings us to the conclusion. We propose extension field cancellation, which is a new multivariate quadratic trapdoor using 2 polynomials of very high degree in the extension field such that there exists a way to combine these polynomials in order to cancel their complexity, in which case you end up with a linear system, and if you solve the system, you obtain the plain text. We propose to use 3 modifiers: Frobenius tail, which was adding this extra term, which unfortunately only works in characteristic 2 and 3, minus, which consists of dropping polynomials from the public key, and projection, which consists of choosing A and B to be singular and n to be prime. In future work, we definitely want to get rid of the minus modifier because decryption is exponential in the number of polynomials you drop. If you can find a way to overcome this drawback, decryption can potentially be very, very fast. Also, the security argument is not entirely rigorous. It does mirror other security arguments for similar systems, but maybe you can shave off a couple of bits or shave on a couple of bits depending on the way the logic goes. And of course, we'd like to shrink keys and figure out how stuff works if you have access to much more parallelism than you do in software. So that's my presentation, and I'll open up the floor for questions.
Any questions?
So when you mention algebraic attacks, so it includes, so algebraic attack against this type of scheme include key recovery and message recovery. And so here I'm confused when you show timing. What is the type of attacks that you consider?
Only message recovery.
Okay, but so
we didn't look at key recovery.
Because in the key recovery, so what you can do here, so you have the min rank. Well, of course, on the parameters that you choose, it's probably fine. But do you try to see if there is a, so to speed up a little bit the key recovery attack, one trick is to have a look on equivalent keys. And this allows to speed up the key recovery attack.
That's a great suggestion. We'll look into that. Thanks.
Yes.
Okay, so maybe if I listened correctly, then I didn't agree with you at the beginning. You say you choose two matrix to be commutative. So if you choose two matrix is commutative, then you don't really need to map it to the extension field. So what you use the commutativity is in the level of extension field, right?
So
because at the beginning you say choose like two matrices to be like they are commute each other, which I don't agree with.
A and B should not be commutative.
Yeah, because at the beginning I heard that you choose two matrices commutative.
So A and B are completely random except for the fact that their rank equals n minus 1 and that their kernels intersect only at the origin. What you want to be commutative is the matrix you obtain after you embed A times X and B times X in the extension field.
Okay, yeah. And so in your security analysis, so you try to destroy the differential attack. So you choose like the size of the matrix to be prime and the rank is like n minus 1. But if you don't use that condition, then you already mentioned that the differential attack doesn't apply to your scheme, right?
Yeah. So there is a theorem by Smith-Toney that this differential invariant exists if and only if your system can be described as a monomial. Our system, with overwhelming probability, cannot be described as a monomial, so this invariant doesn't hold. But maybe there exist other invariants.
That's only if they're multiplications.
That's only if they're multiplications.
It's specifically for that. You can have linear symmetries if you are allowing maps other than multiplications for the elements.
Right.
Yeah. Okay. I'm just not sure. It didn't seem like what you said was right. Maybe I misunderstood you.
Okay, thank you.
Did you not consider the effect of adding vinegar variables, vinegar terms here? Shouldn't you not consider it here? It seems like
Because dropping polynomials and adding vinegar variables has roughly the same effect on increasing the running time of the Grosvenor basis algorithm. Yeah, but essentially that doesn't change the problem because you still have to guess the value of the combined vinegar variables. Of the vinegar variables, you still have to guess their value before you can establish the linear system.
I see. Thank you.
Implementation results. Please show the. Okay. On this slide, and I wonder that the encryption speed is too fast, but decryption is slow. Because the public key size is greater than the secret key, so I thought that the encryption is too slow. Why? The implementation you use C++, so your implementation uses the language of the C++. If I've implemented Magma, I think that the encryption is too slow. Why not?
Okay, that's good news.
Why encryption is too fast, very fast?
Of course, Magma has specialized Gaussian elimination, whereas I just implemented Gaussian elimination by hand.
Your implementation is very great, good. Nice
That might be the
implementation.
reason.
So, thank you very much.
Let's thank the speaker again.